Hello, everyone. In this video, we will discuss some of the problems that are given at the end of chapter 19 in your text. And the subsequent videos, we will also look at the problems from chapter 19b and c. So just a quick recap of chapter 19a lecture video. So we have discussed some of the phenomenological relations. So these relations that describe some of the empirical observations, such as the movement of matter or a movement of energy along with matter. And we also looked at the retarding force, which is nothing but the viscosity or inertia of motion. And based on these three relations, we also discussed some of the transport properties, and we derived equations for diffusion coefficient, thermal conductivity, and viscosity. At the end of the chapter, we also discussed about the rate of effusion, which is nothing but the movement of water if you make a hole in a container having a gas. So we derived all these relations, and we also discussed how these transport properties depend on the physical system's condition, such as its dependence on temperature and pressure. So we would like to use some of these equations in solving some problems which are relevant in day-to-day life. All right, let's look at the first problem. So explain how Fick's first law arises from the concentration gradient of gas molecules. So this is kind of the derivation that we discussed in the lecture video, but let's look at it once again. So one equation that we already derived is basically we need to derive this equation from a physical systems point of view. So let's imagine there is a container. Let's imagine there is a rectangular container here with the gas molecules present in it. So let's say this is z is equal to 0 position and z is equal to some position, let's say at infinity. So the concentration gradient of these molecules, the concentration of the molecules is higher at z is equal to 0 position right here. And as we go along z direction, it reduces. So if you look at a graph in terms of density, number density of the molecules n versus the direction z, the graph as it continues and it's a smooth function, it decreases. So the movement of matter from 0 to a, a point from at 0 to a to at a point later at a higher z value, so it's directly proportional to basically the matter flux is directly proportional to the change in the number density or the concentration of molecules or atoms along the z direction z. So to remove the proportionality constant, so we introduced a constant called diffusion coefficient, and it becomes so. So why did we include this negative sign along with the proportionality constant? Suppose imagine like as we go from z is equal to 0 to z is equal to infinity, the concentration, the number density decreases. So this derivative becomes negative. So to cancel that negative sign, we include an extra sign here with the proportionality constant so that the overall matter flux is a positive thing. So this is negative. To make it negative a positive thing, we included an extra negative sign here. All right, let's look at next problem. Provide molecular interpretations for the dependencies of the diffusion constant and the viscosity on the temperature, pressure, and size of the gas molecules. So to look at this, so we are asked to find the relations between diffusion coefficient and the viscosity, or rather its dependence on the parameters like temperature, pressure, and size of the gas molecules. So D and N are strongly related to temperature, pressure, as well as the size. But we describe size in terms of the collision cross section sigma, which is nothing but pi times d square, where d is the diameter of the molecule if we consider it as a spherical molecule. So we also derived an equation where d is equal to 1 over 3 lambda nu mean. You can also look back in your text. So from your chapter 1 of the Atkins book, the mean free path of the molecules lambda is defined as in terms of sigma as follows: kT over sigma p, where sigma is the collision cross section, p is the pressure, k is Boltzmann constant, and t is temperature. And we also looked at nu mean, which is nothing but 8 RT over pi m power half. So I'm going to include these two equations. Let's say this is 1 in equation 1, and this overall thing becomes kT over sigma p and 8 RT over pi m power half. So if I solve, oh, let's leave it like that. We don't have to solve this equation right now. But if you look at this, so D is inversely proportional to pressure, and also D is directly proportional to T power 3 half, because we have one T outside the power half and there's one T here, becomes total directly proportional to T power 3 halves. And we also, if you look at the sigma, it's again inversely proportional to, D is inversely proportional to sigma, or in other words, D is directly proportional to 1 over pi d squared. Now, once we derive this, we can understand how the diffusion coefficient is depending on all these parameters. So as the pressure increases, the diffusion coefficient decreases. And as the temperature increases, the diffusion coefficient increases. And as the size of the molecule, that means the diameter of the molecule increases, again the diffusion coefficient decreases. So if you look at these ones, if you increase the temperature, let's say the molecules move randomly, and they tend to go move faster, which makes sense. And if you have a larger molecule, they are hard to move from one point to the other, so the diffusion coefficient is kind of less as we increase the size of the molecule. And if you increase the pressure, the change in the concentration decreases, so the diffusion coefficient again decreases. And this is one of the main equation that we use a lot. This equation, we use that in many more problems that are coming here. So please take note of this equation. So I just put it here. So far we discussed about the diffusion coefficient. We also have another term, that is viscosity. So from our previous discussions in the lecture video, we found that eta is equal to P times md over RT. So from the previous equation where we derived some sort of equation for diffusion coefficient D, I'm going to replace this D by that. So it becomes Pm over RT times Kt over 3 sigma P times 8 RT over pi m power half. So we can cancel few of the terms here. So this pressure and this pressure term gets cancelled. T and T gets cancelled. So what's left out here is K over 3 sigma, and I'm going to take this M and T, M and R into this power, and then we rearrange this term. It becomes 8mt over pi r power half. Right. This is also another equation which we use quite a bit. Make sure that you know this. And if you look at this equation here, eta is directly proportional to t power half, because this is t power half here, and eta is also directly proportional to m power half, that is mass, molar mass power half. And of course, there is no pressure term in this equation, so eta is independent of pressure. So independent of pressure. Again, as you increase the temperature, the viscosity increases by a power half. And if you also increase the molar mass, as the molecular mass gets bigger and bigger, the viscosity coefficient is going to be bigger and bigger. So this is how the diffusion coefficient and the viscosity depends on the temperature, pressure, and the size of the molecules. Next, look at the other problem. What might be the effect of molecular interactions on the transport properties of a gas? So what are the different transport properties we have seen till now? It's the diffusion coefficient. Oops, my bad. All right, so it's the diffusion coefficient, thermal conductivity, and the coefficient of viscosity. How do these depend on the interactions, molecular interactions? Of course, any property that we study has an origin from their molecular or atomic interactions. So one equation that we already knew is lambda is equal to kT over sigma p. So sigma, this collision cross section, is a very important parameter when we study these interactions. Let's say if you take it in a box, few molecules, if there are attractive interactions between any two molecules, then they tend to stay closer, right? They tend to stay closer, and they don't leave from here. They don't move from each other. So the collision cross section, that is the number of times or the probability of a molecule colliding with other molecules, is less. So during the attractive forces, when there are attractive forces, the sigma parameter decreases because they don't move a lot. But when we have a repulsive forces, the molecules do not like to come near to each other. So in that case, they move far from each other. In that way, they collide with many more molecules around. So the sigma increases. And if you substitute this lambda parameter into each of these equations, d, k, and n, you can see that everything is inversely proportional to sigma. D is inversely proportional to sigma, and kappa is inversely proportional to sigma, as well as eta is inversely proportional to sigma. So as there are if there are attractive interactions between molecules, the sigma parameter goes down. Then all of these transport properties increases with the attractive forces. Whereas if there are repulsive interactions between molecules, the sigma parameter increases. Well, and as a result, the transport properties go down. So this is how This is how the molecular interactions affect the transport properties of matter. Next question. So calculate the thermal conductivity of organ whose heat capacity, molar heat capacity at constant volume is 12.5 joule per Kelvin per mole, and that the collision cross section sigma is equal to 0.36 nanometer square at 298 Kelvin. So whenever a question is given, write down what is given and what we have to find. We are given C sub Vm and collision cross section, and I converted the nanometers into meters square, basically the SI units. And we know one equation which connects the molar heat capacity at constant volume to the thermal conductivity kappa. But in this equation, if you look at this equation, we don't know what is sigma and what is nu min. In our first problem, we substituted these two relations back into kappa, and then we found out one equation, and that is so kappa is equal to 1 over 3 kt over sigma p times 8 RT pi m over half. So I substitute the new mean, and for lambda, this J value is nothing but the molar concentration, and in this case, J is nothing but the organ, and again, we still have CVM. So we have this equation. So in this equation, we don't know, the question did not talk about P, pressure. So we need to tweak this equation a little bit to find uh, to bring it into those variables that we know of. So let's talk about this. So lambda is equal to kt over sigma p. We know two relations from our physical chemistry knowledge, where odd is equal to a Pietro number times the Boltzmann constant k. Then if I redefine it, k is equal to r over na. And from the ideal gas law equation, PV is equal to nRT. Then what I would say is, I would say N over V, which is nothing but the moles over volume is nothing but the molar concentration. In this case, it's argon. And this is given as P over RT. So, so from this equation here, I can take the P onto the left hand side because I want to replace P, which is equal to molar concentration of argon times RT. Or I'm going to substitute P and K into back into this equation. So it becomes R over Na times T over sigma RT argon. Alright, we have many more common terms, so we can cancel all of them. RT, RT gets cancelled, and it becomes 1 over sigma Na. Yeah. So that's our lambda. So we're going to replace this entire term by this. Okay, when we do that, we get kappa value as 1 over 3, 1 over sigma Na AR, and 8 RT over pi m power half. We still have another argon term from the above and CVM. Again, if you look at, we have a common term here which we can cancel. So this argon and this argon gets cancelled. and the equation is going to be 1 over 3 times 1 over sigma Na 8 RT pi m power half CVM. So at this point of time, we know most of these parameters. R is equal to gas constant 8.3145 joule per Kelvin per mole. And we know temperature from the question 298 Kelvin. Molar mass of argon is 39.95 gram per mole. But we have to convert this into kilogram per mole just to make sure that everything is in the SI units. So kilogram per mole CVM is equal to 12.5 joule per Kelvin per mole, and we got sigma, the collision cross section as 0.36 times 10 power negative 18 meters square. So it's easier, straightforward to plug in all these values into this equation here to arrive at the kappa value. Please try it out. So when we do that, you should get kappa as 7.6 times 10 power negative 3. So, okay, mathematically this is correct, but what are the units? Let's look at them. So if I again think about the kappa equation where we had first CV, let me rewrite it to avoid any confusion. Kappa is equal to CVM over sigma Na. We have 1 over 3 here and 8 RT over pi m power half. So let's do this. The unit for molar heat capacity at constant volume is joule per Kelvin per mole, and that of sigma is meter square, and Avogadro number is generally just per mole. Then we have R gas constant, again joule per Kelvin per mole, and we have temperature in Kelvin. Pi is unitless and mass is kilogram per mole. All right, we got some common terms to take care. Mole per mole and per mole gets cancelled. Kelvin and per Kelvin gets cancelled. Again, per mole gets cancelled. Here we can convert joule into SI units, where 1 joule is equal to kilogram meter square per second square. So once we do that, it becomes joule per Kelvin over meter square times kilogram meter square per second square over kilogram. Okay, I just forgot about this. We still have a half, and this becomes joule per Kelvin over meter square, and this entire term becomes meter per second because of the power. So 1 m here, what cancels gets cancelled with 1 m. So the overall units becomes joule per Kelvin per meter per second. So these are the units for the thermal conductivity kappa. Let's look at some of the problems that we have already on based on the thermal conductivity. So in this problem, we have to calculate the flux of energy arising from a temperature gradient of 10.5 Kelvin per meter in a sample of argon, in which the mean temperature is about 280 Kelvin. So what's given? What we know is kappa, and we kind of derived an equation for kappa as this one. And here we need to calculate the flux and not just the thermal conductivity. So the flux of energy or thermal motion is given as minus negative kappa times dt over dc. And what's given in the uh, question, we know that dt over dc temperature gradient is 10.5 Kelvin per meter, and cross section of organ is this one as we noted in the previous question. So this is also from the previous question. Temperature is given as 280 Kelvin, and we know the gas constant. So at this point of time, it's pretty much straightforward. You plug in all these values since you know CBM, sigma, R and T, and molar mass of argon, which is 39.95. Make sure that you have this in terms of SI units, kilogram per mole. So you plug in all these values, you should get the answer as 7.4 times 10 power negative 3. Again, what are the units? Joule per Kelvin per meter per second. Now, going back to the flux, we have to calculate the flux. So J is equal to minus kappa dt over dz. It's again straightforward. You just multiply 7.4 times 10 power negative 3 by 10.5. So you should get the answer negative 0.0.078. What are the units again? So let's solve that. So we had for the copper, joule per Kelvin per meter per second, and then we multiplied it by dt over dc, which is nothing but Kelvin per meter. So okay, it's this Kelvin and this Kelvin gets cancelled. The final units for the flux, thermal energy flux, is equal to joule per meter square per second. All right, let's look at the next problem. Use the experimental value of thermal conductivity of neon. So I just provided it here, which is 46.5 times 10 power negative 3 joule per Kelvin per meter per second, to estimate the collision cross section of neon atoms at 273 Kelvin. If we are given the molar heat capacity at constant pressure as 20.786. And we know one equation that relates thermal conductivity with the collision cross section. If you look at this equation, okay, let's put down all the values that we know. So RT thermal conductivity and CPM we know, but in this equation, what we are dealing with is CVM, molar heat capacity at constant volume and not at constant pressure. So we need to derive CVM from CPM. From the thermo class, you should be able to you should remember that there is an equation where CVM is equal to CPM minus or the gas constant. So once we employ this, it becomes 20.786 minus gas constant 8.3145. The CVM becomes 12.472 joule per Kelvin per mole. So now we have CVM. Again, it's straightforward. Plug all these equations back into the this original equation, and you get the copper value as 20.18. Oh, sorry. We need to find not. We need to find. We know the thermal conductivity. What we need to find is the sigma value. I'm sorry. All right. So I'm going to take sigma onto the left hand side of the equation, and it becomes 1 over 3 CVM over kappa Na times 8 RT over pi m over half. So now this is relatively straightforward. You plug in all these values, and one thing I forgot, Molar mass of neon is 20.18 times 10 power negative 3 kilogram per mole. So plug in these values, you get sigma as 7.95 times 10 power negative 20. Oh, my bad. So the answer is 7.95 times 10 power negative 20 meter square, or you could say it's 0.0795 nanometer square. So that's the collision cross section of neon. Right, let's get to some of the practical problem that we encounter in our day-to-day lives. So, in a double glazed window, the panes of glass are separated by 1 centimeter. Let's say that this is a window with two glass panes, which are separated by 1 centimeter. What is the rate of transfer of heat by the conduction from warm to exterior cold through a window of area 1 meter square? Let's imagine this is 1 meter square area, and on this is the hotter side, which is at 28 degrees Celsius, and the exterior is at minus 15 degrees Celsius. So, what power of heater is required to make good the loss of heat? So, we are using a heater, and how many wattage that heater should contain to make the loss through the window. Assume that there is a nitrogen in between the panes, so whose thermal conductivity is this 1.0240 joule per Kelvin per meter per second, and we need to solve basically what is the rate, the flux of thermal energy from that is being transferred from the pane in the interior to the pane of the exterior. So for that we need to use kappa and dt or dc. Once we find the energy flux, we need to find the energy, which is nothing but the flux times the area. So let's look at this. So first and foremost, we need to find the gradient. So dt over dc, which is nothing but the t final, or t final minus t1 over the distance between the two panes. So the exterior is final, which is minus 15 and minus 28 over the distance 1 centimeter, but I'm converting that into meters. That is 1.0 times 10 power negative 2 meters. So the units is Kelvin per meter. So here we don't have to convert the Celsius into Kelvin because the difference is still going to be the same. It doesn't matter whether the units are Celsius or Kelvin. So if you solve this one, we get dt over dz as negative 43 times 10 power 2 Kelvin per meter. Now we know the thermal conductivity of nitrogen is this one. So we know kappa value, and dt over dz is just we need to plug in all these values into the J equation, which is negative kappa times dt over dc. Just try to pause the video and then plug in these values and find the answer. Once you do that, we should get the flux. J is equal to negative 0.0240 times 10 power when negative 43 times 10 power 2. So we should get 1.032 times 10 power 2. It's 103.2. If you look at the units, it's joule per second. Or approximately, we need a 103 wattage heater to keep our room constantly at 20 degrees Celsius to make the heat that is lost by uh, by transferring into the other pane, which is on the exterior. So the next question is, calculate the diffusion constant of argon at 20 degrees Celsius and at different pressures, 1 Pascal, 100 kilopascal, and 10 megapascal. If a pressure gradient of 1 bar per meter is established in a pipe, what is the flow of gas due to diffusion? So the question asks for two parts. One is we need to calculate the diffusion constant of argon, and we also have to calculate the flux of matter. What is the flow of argon in a pipe? All right, some of the constants that we know, that is the gas constant. We know temperature is 20 degrees Celsius, converting that to Kelvin to 93.15. We know the cross section of argon, 0.36 times 10 power negative 18 meters squared, and the pressure gradient dP over dC is 1 bar per meter. We need to convert that into common units since we have to find the diffusion coefficient at Pascal. So let's convert bar into Pascal, which is nothing but 1 times 10 power 5 Pascal per meter. And molar mass of argon is 39.95 times 10 power negative 3 kilogram per mole. And this is the Boltzmann constant K. So we derived this equation that relates the diffusion coefficient to different parameters like temperature, pressure, and the collision cross section in our first problem. So I just pulled it here. We know all these parameters except for the pressure. When we know the pressure, that's what we need to input for different pressures and then find the diffusion coefficient. So let's try to find a generalized equation. So I substituted all of these terms here except for the pressure, and then I calculated it. So I end up getting D is equal to 1.48 times 1 over 3, and we have to input pressure in terms of Pascal. Now, if we were to input the pressure in Pascal, so what should be the units of the diffusion coefficient? So we need to find that. All right, I pull this equation once more to calculate the units for this. So the first one is the Boltzmann constant K there, so which has the units of joule per Kelvin, and then we have temperature again here over sigma is nothing but meter square, and pressure we need to we have it in terms of pascals for now. Okay, and the gas constant is joule per Kelvin per mole times again Kelvin per temperature, and mass is kilogram per mole. We sort of solved this in one of the this term in one of the problems, and there are some terms which we can cancel. So per Kelvin, Kelvin gets cancelled here. Per Kelvin, Kelvin, mole and mole gets cancelled, and joule we can convert that to kilogram meter square per second square. So the final equation here is, I mean, we can also convert this into SI units. So let's say kilogram meter square per second square over meter square. Again, this is still in terms of Pascal times this whole term becomes meter per second as we have seen in the other equation. So again, we have got a few terms to get cancelled. These two gets cancelled, and the final equation is kilogram uh, meter per second cube over Pascal. One thing that we need to know, we can write Pascal uh, in terms of kilograms meter second. So that is equal to 1 Pascal is equal to 1 kilogram per meter per second squared. So I'm going to replace that here. Kilogram meter per second uh, uh, power negative cube over kilogram per meter per second squared. So these two terms gets cancelled, and we have 1 per second here, and this becomes a meter square. So the overall units for diffusion coefficient is going to be d is equal to in terms of meter square per second. So if we input the pressure in terms of Pascal, so these are the units of diffusion coefficient going to be. So yep, these are the units. So you have to write it as d is equal to 1.48 times meter square per second times 1 over p in terms of Pascal. So let's pull that equation here. Once we know that, the game is not at over. So we just found the diffusion coefficient for at a given pressure. So we need to do a little bit more for this. So we need to find the flow of argon gas in a pipe. For that, we need to make use of the flux equation. So we know that matter flux is J sub Z is equal to negative D and the derivative of number density with respect to the position. So this is the matter flux, the movement of molecules per area per unit time. If you want to calculate the flow, if I divide this by Avogadro number, I get this in terms of moles. So that's the flow. So I divide both sides of the equation with the n sub a Avogadro number, and let's rewrite this j sub z over Na is equal to minus dNa, and I like to change the number density into something else because we don't have the number density to calculate it. So go back to the ideal gas law equation. PV is equal to nRT, and N over V is equal to P over RT. So if I multiply Avogadro number and moles, it becomes number of molecules over V, which is nothing but the number density, and P Na over RT. Since we multiplied Na on the left hand side, we have to do the same thing on the right hand side. So I got this equation, number density is equal to this. So I can replace this term instead of number density. So it becomes d over dz times p na over rt. And they, again, this equation, we have these terms as constants, na, rt. So we can take them out of the derivative. So it becomes minus d na over na rt dp over dz. Again, this na and this na gets cancelled, and the flow of organ z sub c over na is equal to negative d over rt times dp over dz. So now we know the diffusion coefficient as we calculated from the previous equation, or until we know dp or dz is also given in the question, so we can straight away plug in all these values and then find the answer. So if we do that, you end up getting the answers as at p is equal to 1 Pascal, diffusion coefficient is 1.5 meters square per second, and the flow is minus 61 mole per meter square per second. Again, you need to find the units when you calculate the flow. So if you look at, as we increase the pressure from 1 Pascal to 100 Pascal, 100 kilopascal, and then to 10 megapascal, the diffusion coefficient is decreases by a lot. Okay, the changes, there is a 4 orders of magnitude change, and then there is a 6 orders of magnitude change from when we go from 1 Pascal to 10 megapascal. At the same time, as the diffusion coefficient decreases, the flow of argon also is decreasing by similar magnitudes. So as we noted in our as one of the discussion problems, where As we increase the pressure, the diffusion coefficient decreases and the flow also decreases. All right, let's go to the next problem. Use the experimental value of coefficient of viscosity. So we know the coefficient of viscosity is this 298 times 10 power negative 7 kilogram per meter square per second to estimate the collision cross section of neon. So what's given? R is we know, T we know, coefficient of viscosity eta is given, and molar mass is we know that molar mass. So eta is, we know one equation that eta is related to diffusion coefficient, and diffusion coefficient is related to the sigma, which is the collision cross section that we need to find. So we can rearrange this equation to find the collision cross section. Again, we have to do a bit of mathematical jugglery here. So this equation we solved from before, and we also solved this equation, right? We also derived, we substituted this d in this one, and we end up with the k over 3 sigma times 8 mt over pi r power half. So this is the equation that we got in one of our previous problems. So once we get this, it's a straightforward thing. We can substitute all of these. Boltzmann constant is 1.381 10 power negative 23 times 3 times. Okay, one thing that we need to do is we need to swap this. We need to find the sigma and not the coefficient of viscosity. So we will swap these two. So it becomes sigma, and then eta is equal to 298 times 10 power negative 7, 8 times 20.18 times 273 uh, times 10 power negative 3, because the molar mass is in terms of kilograms, and it's 3.14 times the gas constant 8.3145. Right, you can solve this math. So you should get 2.01 times 10 power negative 19 meters square, or 0.201 nanometer square. So given the fact that if the diffusion coefficient or the viscosity is given, we can calculate the collision cross section, or if the collision cross section is given, we should be able to calculate the transfer properties. Let's look at the next problem. Calculate the viscosity of air at different temperatures. If we are given the collision cross section of air as 0.40 nanometer square, the experimental values are 1. So they have given some of the experimental values of the viscosity of air at different temperatures. We need to find this mathematically from the basic equations, and then cross-check our answers with the experimentally determined values. So what's given here? The collision cross-section of air, uh, 0.40 times 10 power negative 18 meters square, and the molar mass of air is 29 times 10 power negative 3 kilogram per mole. So we already know this equation where the viscosity eta is related to sigma, as we solved in the previous problem. And pretty much we know the rest of the parameters here, except that we need to keep swapping the temperature for different values and then calculate the viscosity. So before we do this, we have to, so whenever you are asked to do the same mathematics by different values, you need to derive a general equation. So what we can do is we can substitute all these parameters. 1.381 times 10 power negative 23 over 3 times sigma 0.40 times 10 power negative 18, and here this is the 8 times molar mass 29.0 times 10 power negative 3 we'll leave the temperature as it is, and but we have to input this in terms of Kelvin. Divided by 3.14 times 8.3145 as the is the gas constant, the whole thing power half. So if we solve this term, this entire term, except for the temperature, make sure that you include the power half for all these terms. So when you calculate this, you get 1.08 times 10 power negative 6 kilogram per meter per second times the temperature, which you have to input in Kelvin power half. Don't misunderstand for the Kelvin power half. It's nothing to do with the units. It just indicates that the temperature needs to be inputted in terms of Kelvin and not Celsius. Suppose if you want to do this, convert these units in terms of poise, it becomes 1.08 10 power negative 5 poise times temperature in Kelvin power half, because 1 poise is equal to 10 power negative 1 kilogram per meter per second. So now you got this one, and if you replace the temperature with different values, you should get these answers: 180, 178 micropoise, 186 micropoise, and 342 micropoise. Another challenge here is we are given these are the calculated values, but we are also given the experimentally determined values. This is the experimental. So at 273 Kelvin, we experimentally it was found it's 173 micropoise, and at the 298 Kelvin it's 182 micropoise. At well, this is at 1000 Kelvin, but we are given at 600 degrees Celsius, which is at 394 micropoise. So it seems like when we increase the temperature, the viscosity, the coefficient of viscosity has to increase because it has a direct dependence of T power half. So as we increase the temperature, the viscosity is increasing. However, when 1000 Kelvin, which is approximately 770 Celsius, it's 342, but experimentally 394 micropoise is determined at 600 degrees Celsius. So maybe at a higher temperature, this equation doesn't hold good, and we need to do a lot of other approximations to make sure that our equation is accurate at all temperatures. So let's look at a problem that deals with the collision flux. A solid surface with dimensions 2.5 millimeter and 3.5 millimeter. Let's say it's exposed to argon gas at 90 Pascal and 500 Kelvin. And let's say this is the surface with these dimensions and it is exposed to argon atoms. So how many collisions do the argon atoms make with this surface in 15 seconds? So when you are talking about collisions, one thing that needs to come into our mind is the collision flux. Z sub W is P over 2 pi m kT power half. And I listed the parameters that are given in the question, and we know some of the parameters of the argon. So here, in this case, don't get confused with M here. This is not molar mass, this is mass. So we don't know the mass of argon, so we need to again do some mathematical rearrangements to arrive at an equation which contains the parameters that we know. Again, using some of the known values, we know that K is equal to R over Na, and mass is equal to molar mass divided by the Avogadro number. So I'll make use of these two equations. So P over 2 pi instead of M m, I'm going to use molar mass, or Na, times K instead of K, use R over Na, times T power half. So the entire equation becomes P times Na over 2 pi mRT power half. Again, so this is basically this one. We use this equation quite a lot in most of the problems that are related to the collision flux. So once we have this problem, we just need to plug in all the values that we know, and that is, say we know P is 90 pascals times Avogadro number 6.032 10 power negative 23 over 2 times 3.14 times 39.95 times 10 power negative 3 times 8.3145 times the temperature 500 Kelvin over power half. So this is Z sub W, which indicates that if you look at the previous slide, so the collision flux, the number of molecules, organ molecules that are hitting the surface per unit area in per time or per second. What we need to know is total number of collisions that happens over this area, the entire area, in 15 seconds. So all we need to do is we need to multiply Z sub W with the area and temperature. So it becomes Z sub W, area of the surface, and the time that we wanted to calculate. So from the dimensions of the surface, 2.5 and 3 point millimeter, we can calculate the area, which which is length versus length times spread. So it's kind of easier to calculate. So once we can get the area as 7.5 times 10 power negative 6, and the time is 15 seconds. Now we just solve this math. Get 1.9 times 1.9 times 10 power 20 collisions will occur on that surface in 15 seconds. Let's look at a similar problem. An efficient cell has a circular hole of diameter 2.5 millimeter. Let's say this is a cell and there is a hole of 2.5 millimeter, and I converted a diameter, and then I converted that to radius 1.25 times 10 power negative 3 meters. If the molar mass of the solid in the cell is 260 gram per mole, and its vapor pressure is 0.835 pascals at 400 Kelvin, by how much will the mass of this solid decrease in a period of 2 hours? So obviously there is a hole for the cell, and the solid sample will vaporize based on its vapor pressure, and the molecules will come out of it. And while doing so, there will be some mass loss. So we need to find that mass loss. So how do we calculate the mass loss? Let's imagine, like, so obviously it depends on the flux or the movement of the molecules out of this hole, which is nothing but, again, which depends on how many molecules from inside the container are hitting this, going through this hole, and it's basically nothing but the collision flux over the wall, which is Z sub W. But we need to restrict that to the area of the hole. So the area of the hole A, and the time, if you want to calculate how much uh, like how much time you want to calculate this problem for. And of course we need this is the number of molecules that are going out of it. So we need to also find the mass of those molecules. It's not molar mass, just mass, to determine the entire mass loss, right? So z sub w, as we calculated, as we derived in the previous problem, it's p times na over 2 pi m RT power half. We know area times time, and m can be written as molar mass over Na. So this Na and this Na gets cancelled. So this we can rewrite as P8 T times this m can go into this power, and it becomes m over 2 pi RT power half. So again, this is straightforward. From here, we just need to plug in all the values. So m loss is equal to 0.835. That's the vapor pressure times area. Area of this hole is nothing but the pi r square, right? So I will write that instead of calculating that separately. 3.414 times 1.25 times 10 to the power negative 3 uh, square, power squared, uh, times the time, which is given in 2 hours, but I need to convert that into seconds. 2 times 3,600 seconds. And we have the other term. This is the molar mass, 10 power negative 3 in terms of kilogram per mole, over 2 times 3.14 times 8.3145 times the temperature, which is 400 Kelvin. So again, you calculate this math, you should get 1.04 times 10 power negative 4 kilograms, or approximately equal to 104 milligrams. So if we just have a hole in a cell at 400 Kelvin, we will have a loss of 104 milligrams of this sample, because there is a hole for the cell. All right, let's look at another problem. It is kind of similar to the previous problem, but it's a slightly, we need to find a different thing. A solid compound of molar mass 100 gram per mole. So this is 100 gram per mole. This one was introduced into a container and heated up to 400 degrees Celsius. And when a hole of diameter 0.5 millimeter was opened in the container for 400 seconds, a mass loss of 285 milligrams was measured. So here they have given the mass loss, and we need to calculate the vapor pressure of the compound at 400 degrees Celsius. So I converted the diameter into radius and millimeters into meters. There's a mass loss, well deltoid molar mass, and we know the mass. Okay, so we know this equation that we derived in the previous problem. All we need to do is we need to rearrange. So get this to the left hand side. So it becomes mass loss over AT times 2 pi RT over M power half. Again, this is now a straightforward problem. So mass loss is 285, 10 power negative 6. I just converted the milligrams into kilograms, over area is pi 3.14 times 0.25 times 10 power negative 3 square, multiplied by 2 times 3.14 times 0.145 times 673, converted the 400 degrees Celsius into Kelvin, over this is the molar mass, again converted that to in terms of kilogram per mole. Solve this math, should get the pressure as 2.15 times 10 power 3 pascals. Check this answer. Basically, at the end, you get the units as kilogram per meter per second square, which are nothing but the pascals. Well, let's look at the next problem. A manometer was connected to a bulb containing carbon dioxide. Let's say the cylinder that you're seeing on your right, this is the bulb, and a manometer is connected to that. And this is filled with carbon dioxide. The gas was allowed to escape through a small pinhole. Let's say this is a pinhole, and the time for the manometer reading to drop from 75 centimeters to 50 centimeters was 52 seconds. So this is 52 seconds. And if they repeat the same experiment with nitrogen, whose molecular weight is 28.02 gram per mole, the same fall from 75 centimeters to 50 centimeters in the manometer reading happens in 42 seconds. So we need to, from this information, we need to calculate the molar mass of carbon dioxide, which is very interesting. So to solve this problem, we need to derive few equations. Obviously, uh, we have to calculate some term that depends for the pressure that depends on the time, right? And when we make a hole in this bulb, there is an efflux of the molecules out of this hole. So which is basically nothing but the effusion, right? And we know that it is directly proportional to the gradient, the number density gradient, from inner to the outer side. Again, we don't know the number density. We need to use other equations. In one of the previous problems, we replaced the number density with something else, right? So it becomes dt d over dt, and n becomes pv and a over t. I mean, if it gets confusing, let's solve this here. Uh, Assume that let's start with ideal gas law equation. PV is equal to nRT. Then I make it N over V is equal to P over RT. I multiply both sides of the equation with Avogadro number so that this whole thing becomes this becomes number density. So that is number density. N over V is equal to P NA RT. And from this, if you want to just take what is N, it's PV NA over RT. This is from here. I just substituted this equation instead of N. So at this point of time, we have minus d over dt. Again, one thing that I wanted to tell you is don't get confused with the flux. The flux depends on it's a derivative of with respect to the position. Here we are dealing with the time, the rate at which the molecules from inside the bulb comes out of it. That's the effusion, right? And in this one, we have few constants here. Na, V, volume, Na, R, and T are all constants in our case. So they just come out of the derivative. V Na over RT times dP over dt. So this entire equation is for effusion. So from our lecture video, we saw that we can write effusion as, let's say, effusion as PA and A, because that's the area. We consider the area. So the number of molecules that are coming out of the pinhole times the collision flux, basically. 2 pi mRT power half. So we got this equation to solve and arrive at the equation that we wanted. So let's do that. Probably I might need to rewrite this. 1 second. All right. So it's VNA over RT times times dp over dt is equal to PANA 2 pi m r t power half. So this Na gets cancelled on both sides of the equation, and I want only dp over dt on the left hand side so that I can take the rest to the right hand side. So it becomes minus PA RT over V times 1 over 2 pi m RT power half. So here I can take the RT back into this power half so that the entire equation becomes PA over V times RT over 2 pi m power half. So I can rewrite this again as dp over dt is equal to uh, well let's write it in the next slide. So I can rearrange the previous equation so that I get the pressure terms on one side and the time terms on the other side. So tau, where tau is nothing but the rest of the term v over a 2 pi m rt power half. Just to make sure, just this term here, and this is the reciprocal of the tau is a reciprocal of the term that we saw in the previous slide. So once we get this one, we can take integrals for this equation. So I can take integral for both of these equations from p0 to p, and here from 0 to time t. So I get ln p over p naught is equal to minus t over tau. Or we can rewrite this equation as p of t is equal to p sub naught at time t0 e power negative t over tau. So once we are at this position, and tau is also called as the relaxation time. It's called relaxation time. So I can calculate the relaxation time for the nitrogen, which is, if you consider this equation, relaxation tau and 2 is nothing but uh, here we don't have to consider negative sign because time is going to be a positive one. So for just the calculation purpose, I can disregard the negative. It's basically t, uh, the time the manometer takes to fall from 75 to 50 centimeters over ln p over p naught. So which is nothing but 42 seconds divided by ln 75 over 50, which is equal to 103.58, or it's a 104 seconds. So in a similar way, we can also calculate this for carbon dioxide, which is time the manometer takes to drop from 75 to 50 centimeters, and p over p naught, which is nothing but 52 over ln 75 over 50. So this is, if you calculate this, becomes 128 seconds. So if you look at the relation tau, so tau is directly proportional to m power half. So we're going to make use of that. So tau is directly proportional to m power half. And I can, since I have tau for CO2 and N2, and I know molar mass of nitrogen. So based on this equation, I can calculate the molar mass of carbon dioxide. So if we do that, so let's say MoCO2, Mn2 power half is equal to tau CO2 and tau of N2. Again, getting the molar mass of carbon dioxide on the left hand side, the rest of the term becomes tau of N2 power squared times molar mass of N2. So just doing the math, 128 seconds divided by 104 seconds whole squared times 28.02. You don't have to convert here to kilograms. You can leave it as grams, and you will get the answer in terms of grams. So it's 42.4 gram per mole. So one thought doesn't compare this value with the value of molar mass of carbon dioxide that we calculate, right? And see what's the difference, and try to explain why there is why what is the reason if there is any difference, right? Compare the molar mass of CO2 from the standard atomic mass units of carbon dioxide. All right, this is the last problem that we're gonna look at. Uh, it's kind of a similar problem. So a space vehicle of internal volume, let's say, pardon me for my bad drawing, but let's imagine that this is a space vehicle. Well, I should say something like that. Ouch. All right, it ended up being something else. Okay. A space vehicle of internal volume. Volume is 3.0 meter cube. Is struck by a meteor. So it's struck by a meteor, and a hole of 0.10 millimeter. Let's say there's a hole here which is of radius 0.10 millimeter is formed. If the oxygen pressure within the vehicle is initially at so let's say P initial is 80 kilopascal and the temperature is 298 Kelvin, how long will the pressure take to fall to PF is equal to 70 kilopascal? So basically we need to determine the time. So as we derived in the previous question, a term tau for the relaxation, which is also called as relaxation time, that is equal to V over A times T pi M or T power half. So we need to find this tau time. One, we know the rest of the parameters here. So volume is nothing but 3 meter cube. Area is pi r cube. Pi times radius is point uh, yeah, back to the slide. 0.1 times 10 power negative 3 meters, and then square. Okay, that's the first part, and the second part is 2 times 3.14 times molar mass, which is oxygen, right? The spacecraft contains oxygen, so 32 points 10 power negative 3 kilogram per mole, 8.3145 times 298 Kelvin, the whole term power half. So if you solve this, they should get 8.6 times 10 power 5 seconds, which is approximately 10 days. So this is not the thing what we want. This is the relaxation time. What we need to find is the time it takes for the pressure to drop from 80 kilopascal to 70 kilopascal. And we saw from the previous answer, from the previous question, the time is given is tau times ln p over p naught. Or in this case, it's p initial or p to that. So it becomes 8.6 times 10 power 5 times ln 80 over 70. Instead of this, you can also use 10 days. If you do the math, you end at the final answer you get as 1.3 days. So in 1.3 days, the pressure, the oxygen pressure inside the spacecraft drops from 80 to 70 kilopascal. So obviously, the design of this spacecraft must be sturdy and robust. Should be able to withstand some of these meteorites that might hit the spacecraft when we during the launch during its stay in space. Hopefully, you enjoyed the problem solving session. I will try to do the problem solving for chapter 19B and C as soon as possible, and then I'll share it with your professor. Thank you. See you all in the next video.